So my name is Andrew Brown. I'm a data scientist at a local startup doing data science for healthcare. The startup is called New Hippo Health. And talk to me about it. It's a really cool company. And I want to get into this because I'm nervous about it. So let's do this. Okay. So I'm going to talk to you today about homomorphically encrypted machine learning. So what is it? What can it do for you? The biggest thing that it's going to do for us is make some inaccessible data, private data, accessible to us for our machine learning models. Things like healthcare data, finance data, they're all locked away and kept in private stores. But homomorphic encryption really is the key to getting access to that and doing machine learning on it without actually getting access to it. So you get possession of it without access. So, like Morpheus said, homomorphic encryption will be the key. But what is encryption? And what is homomorphic? So first, encryption. Encryption is about taking a message and turning it into a ciphertext and vice versa. So you have an example here. This gobbledygook can be turned into data science rules using a decryption method. But the important thing is that you can have a ciphertext without knowing the information that it holds. So you can have possession of the ciphertext without access to the information within it. And that's the important part of encryption here. So what's homomorphic? Homomorphic is about mappings between things. So they go from X to Y, usually something like integers, and it's an operation. And the important part is this, that the operation distributes over addition and over multiplication. So addition and then doing the operation is the same as doing the operation and then adding, same for multiplication. So operations distribute over math is the important thing. So what does this mean for homomorphic encryption? So let's say we have Alice. She has some data. She sends it over to Bob, and she encrypts it on the way. He has possession to it, but he can't access the actual data. He does some math to it, sends that back to Alice, and she can actually just decrypt the answer from what she got sent back. This is not typical of a usual function like x squared or something like that. So this D is doing something funky. And what it's doing is this, that it's actually distributing itself over the polynomial. That the D can actually just go in over addition and multiplication and just distribute over the math, and then you get this out the other side. And D is the other side of the encryption. Encrypt it one way, decrypt it the other way. So that's over polynomials, but what about machine learning? So for that, we need to show that we can do this over matrices, activations, and gradient descent. And then we can basically have machine learning with homomorphically encrypted data. So again, same paradigm. Alice has some data. She sends it over to Bob. Bob applies the matrix M, sends it back. Alice decrypts it and gets out the matrix applied to X. And the reason it works is because matrix multiplication is just a linear polynomial. It's just a bunch of linear polynomial operations. So this works just fine. So for activations, we have some data, again, sent over. Bob applies the activation. She decrypts it and gets the activation applied to X as if she did it. Now, the reason this works in most cases like ReLU and leaky ReLU is that you just have two polynomials that are hinged at 0. And the homomorphically 0 goes to 0, and you have two polynomials, and we already know it works for polynomials. But what about things like sigmoid, you're thinking, right? So go back to your calculus 1, 2 something days. And remember Taylor polynomials. Taylor polynomials are a way to approximate a transcendental function or a differentiable function with a polynomial. So here we can take an approximation, send that across, she can decrypt it, and she gets an approximation of the sigmoid applied to X. Too much time here, speaking too fast. So we can actually do predictions on encrypted data. So data set, send it across encrypted. Bob can run it through a neural net that he has set up. He can get out quasi-predictions of the other side, send those over to Alice, and she can decrypt them and get the real predictions. Now the trick here is that Bob has never had access to the data or the predictions. So he can't do any correlations against the data and can't figure anything out about the data set that Alice wants to keep private. So now gradient descent, the last piece. We have the normal update that you all recognize from your machine learning courses. Exactly the same in encrypted land because we're just talking about numbers. And what you actually get is training on encrypted parameters. So you can actually encrypt an entire neural net just by encrypting each of the values of each of the nodes and decrypt it also. So what does this give us? This gives us a weight. So it gives us training through encryption. Let's change the paradigm a bit. Alice has a public key encryption system with E made public and a model that she sends encrypted over to Bob. Bob has a data set which he encrypts with Alice's key and then does encrypted training on the encrypted neural net, on the encrypted data. He then sends it back to Alice, and now she can decrypt a trained model from Bob. Kind of cool, right? Because she's never had access to his data, and he's never had access to her model. So it's complete separation of what's going on. What's extra cool is that Alice can do this repeatedly. Alice can take this and send it to another hospital, another person, another hospital over there, and they can each go through this process and train on really huge data that no one has to share with anyone else. So that's all really cool. What's wrong? It's really slow, really slow. It started at 100 trillion times slower than a normal operation. They've gotten a lot faster, but it's a big hurdle to get over. The encrypted data is also a lot bigger. There are no floating point operations because it's all integer, so you have to scale everything up, making it bigger. And sequential operations like a neural net forces big primes in the encryption scheme, making it even bigger. So there's a lot of hurdles here to get over. So it's going to be some time before we can actually start using this to do anything. And I give myself too much time again. But it'll be some time before we can take the red pill and actually get to homomorphically encrypted machine learning. But I still think it's a really important technology that you should be paying attention to as a data scientist. Thank you. And there will be some references up here in a second. There you go. Okay, so questions. Let's go with Yves.
Okay, so one concern that I would have is, like, exactly as you mentioned, like you're gonna have to be operating on integers that might be kind of big, and so I would expect in order to actually make it work, you would actually have to do some truncations at some point.
Yes.
So
that's like you have to scale up and choose your level of approximation that you're willing to live with.
So my concern with that would be what would be the impact of that on stability of predictions? Because, like, say, if you have some sort of perturbation in your input, your encryption is forcing some sort of truncation within the network, like when you actually execute the thing, which would actually affect the output. My concern would be, like, how stable is the output with respect to perturbations in the input?
To my knowledge, this hasn't been really done a great deal. This is the closest I've heard about, but it's still not really production ready. So I don't think that's like a real concern yet. I think the concerns are really here still. That we're still talking about the size of everything and dealing with that, and the speed of everything and dealing with that. I think we'll be getting to those. That's another major hurdle that everyone's like kind of going like, I don't know how to deal with that yet, but yeah.
So, and just one more follow-up would be, so how does it actually work? I mean, like, let's say I have, can you give one example of how this actually reflects concretely? Like, say, I have a model that's, I don't know, like, it's a text document, and I'm doing some, I don't know, multi-class classification on that document classification. How the heck, where do you compress things? Where do you encrypt things? Do you encrypt the words, the embeddings?
Yeah, so this is another part of the, like, cryptographic primitives have to be worked out here. My guess would be is that you're going to embed the documents and send that over. Like encrypt the embedding vector and send that.
So you first turn that into a hunk of numbers, and then you somehow do something with those numbers that is going to do that encryption.
That's my guess, yeah.
Okay.
Next. Next, let's go here and I'll get to Matt. Was there anyone at the back? There's a microphone at the back there. You've got it? Okay. Do you want to go?
Quick question. Is Bob the one who is doing the training on the neural net, or is Bob just the infrastructure provider?
It depends on the example. He is generally, Bob in my example was the encrypted land, and Alice was the decrypted land. That's basically, I tried to keep that color the same everywhere, that blue meant encrypted and orange meant decrypted. This changes it a bit because Bob also has some decrypted things that enter the formulation. Does that answer your question?
So Alice is like a hospital or someone who provided the data to Bob to generate
Alice
a
is
model.
more like in this example. Bob is more like the hospital. That Alice is the one that wants to make the model, but doesn't have access to the data. So she's going to go talk to Health Authority 1, Health Authority 2, get some data from both, train it in this way, and never have had access to the data during the process from either. And she's never had to give up her model to either of them either. Cool. Up here at the front.
Thanks.
Does this mean that, practically speaking, there's no breach of consent or privacy when it comes to understanding this data?
That is the ideal, yes. But like most cryptographic anything, once this gets put out into the field, it's going to be really, really hard tested by hackers and other penetration testers and stuff like that. So there's still, once we get to the point where we have a production speed implementation of this and we can actually do things, now we're going to have to start talking about, is it actually cryptographically secure from all these other directions we haven't thought about yet? So we're a ways from that, but that is the ideal, that we get, that we can obey privacy and we don't actually release data in that way. So if you can encrypt communication and that's allowed, this should be an allowable way to move data around as well. Oh, sorry, I'm going to get Matt back there.
Yeah.
Hey, okay, now that I got you. So all the examples here, we're using neural nets. What else would work here?
Anything where the math basically can be converted into a polynomial. Because the only thing you can push across is addition and multiplication, which gives you arbitrary polynomial operations.
So just to be clear, linear regression, yes. Decision tree, no?
Probably not.
Okay.
But I mean, some of this will be, how do you turn your head sideways to look at a decision tree properly so that it becomes polynomial, right? There's going to be potentially some of that out there. Oh, yeah.
I'm hoping this isn't a dumb question, but I'm going to ask it anyways.
Okay.
Wouldn't some embeddings be kind of like encryptions by nature? Like nobody really knows how this embedding works, and that would sort of solve the size problems. If you just send some embedded data to somebody and they don't know how it was embedded, isn't that secure by nature?
Potentially, but we know from neural nets that you can actually extract some examples from within them that were used to train them. So there's this echo of the information that was actually used. And I wouldn't necessarily expect anyone to believe that that wouldn't be possible with an embedding of some document or something like that. Like, we do want it to hold the information that was used to generate it, right? So I still think it's probably, particularly from the healthcare example, they'll want to know that you've taken this step. Yeah. Oh, she was, I think, first. You turned it off, I think. At the bottom.
Hello?
Yep.
Just want to get a sense of how far along, when we can use this. So what?
How long till we can do this?
Yeah, so in the sense of are there libraries that we can play around with?
I looked around and there's nothing in Python that I found. There's some bespoke code that people have written up in notebooks and stuff like that, but no formal PyPI package that I've seen. There are some C or C++ libraries that exist. And so they're out there. Like you can start playing with this stuff if you know C and can set up C. I'm not exactly fluid in that, so.
Second question. So the references you have, what type of problem size are we talking about this can handle? I know you have also a slide talking about the speed.
So all of these, except for CryptoNets, are theoretic papers. So the very first one that actually created the theory behind this was in 2009. So this is new cryptography. This is very new cryptography. The fact that we have some implementation by Microsoft, of course, but they've put a lot of money and research and smart people into it. But this is the first reasonable go at it that I've heard about. And my mind is blanking on what's going on there. But this, it's not production ready. You can't just roll this out and have it work for people. It's way slower and way bigger, and it's hard to legitimize the use of it yet.
Sounds like a reading group paper.
Yeah.
The gentleman to my right, you were asking about, well, can't you just hide it, encrypt it by putting it in an embedding? Earlier today, this gentleman and I were talking about some papers where they take two corpuses of natural language text, English and Arabic, or something like that. And from the two independent corpuses, they can create a bilingual dictionary. And they do this by embedding the two monolingual corpuses separately, and then they learn how to essentially rotate and skew the two different embeddings until they're the same, and then you can see the correlation. So if somebody was doing an embedding of hospital data, if you had a sense of kind of what the model was, how they did that embedding, then you could take your own hospital's data or hospital data from North Korea that you cracked. And then you could do the same sort of transformation and figure out the concordances, and then it's not secure anymore.
Okay, was there any? Okay. I'll get to you in a second.
Two things actually. So on that, I'm not so convinced because, like, say you have an actual sentence embedding. Like even if you actually had access to embeddings of each token, doesn't matter what it is. Like you could do something like that, even if it's an ID encrypted. If it's just like an integer, in principle, you could do something like that. But like if you actually have like an embedding of the sentence, like as a bunch of numbers that it's not basically it's not an injection. Like it would actually destroy information once you will create the embedding. I don't think you can do the way back. In any case, so one question that I would have that I had before that was why can't I just multiply my numerical vector by a random Gaussian matrix, random Gaussian matrix, and I use as my encryption key the random seed, because like you are not going to be able to there are infinitely many representations that you could come back to. Like it's an honest question. I have no idea why. So why wouldn't
is this hard?
Why that would fail?
That's a good question. So one of the implementations I saw was essentially doing like a matrix multiplication as like generating a random matrix and doing that. Why that won't scale or why that won't, I don't know.
Why wouldn't that actually be like
enough? Like why wouldn't that be enough? Don't know. I don't know. I do know like it took a while to get to this though. Like so I suspect there's something wrong with that, but I just don't know what it is. Okay. And in the papers they don't address why they didn't do that, right?
The size of your data is large enough.
Can't hear you.
I don't know with the random Gaussian matrix, if the size of your data is large enough, like if the size of that matrix is large enough, I don't know if it will be easy to decrypt afterwards.
I can extend that to fast matrices.
All right. We'll have discussions at the bar. 10? No, I got questions from Paul. Actually, let's get this guy's question. He's been waiting.
I also want to argue about, question how secure this is. Say you overfit the model a little. Now the neural network or the model that you were training memorized the data to some extent. You unencrypt the model, and now you have access to the data to some extent.
Yep. That's going to be one of the tricks to this, like whether it can actually live up to its promise is an open question, I think. And so those echoes, I don't know how we're dealing with those echoes in general, but that will be a stumbling block for this, for sure. I tried looking around to see if there's any idea of how you might deal with that, and I couldn't find anything. So it's still an open question to me.
So a couple of things from Robin on the live chat. I'm going to take them in reverse order. This last one was just a comment to Evis. He says, like a one-time pad. That's a little out of context now that discussion has passed, but I guess your idea of encrypting with a random Gaussian is like a one-time pad. I think it's the observation. All right, question, again, taking the second question first. If each individual input is separately encrypted with the same scheme, then Bob is able to determine which records have identical inputs. Is this true?
Most encryption schemes have a randomization that's going on, like Diffie-Hellman will throw in a random number into it to make sure that that kind of attack can't happen. For this to work, whatever scheme they come up with and land with is going to have to do the same thing. But it's going to have this random number that changes the number so a 1 doesn't, or a 1 has to look like a 1 under homomorphism, but a 2 doesn't necessarily look like a 2 everywhere that you have it. So that kind of thing will have to go on. And it exists in current encryption schemes now. So it's, I think, an easy addition. There's harder pieces to this puzzle.
And an earlier question, which is a little more general, and maybe you've kind of touched on this, but first of all, he says, awesome talk. Is this encryption scheme, the one described, is it the main or only in the recent literature for this purpose?
No. So fully homomorphic encryption using ideal lattice is the first one, and it's entirely different from efficient vector homomorphic encryption, which is like the one you were talking about. And the practical homomorphic encryption over the integers is different again. So there's going to be a lot of research in this field from a theoretical standpoint, and there's going to be a bunch of useless schemes that people come up with. One of them will land, and one of them will be the right one that turns out to be a nicely implementable thing, but I don't think we have that yet here. One more. Maya, you're the last.
Hello. I guess my question is more high level than this. So how do you know if your model is actually working? I don't know enough models that are so plug and play that you can apply it to any data that doesn't have context and know if it's working or not. It requires actually looking at the results and seeing, is this sensible or not?
Yep. And in the paradigm where the neural network itself, wrong direction, where basically at the end where Alice had sent over the encrypted model, all of the math that you're doing on it to figure out the accuracy and to figure out all the things that are going on it, that's all encrypted. So yeah, it's going to be, what do we do? Who knows? Maybe you send the accuracy score over to Alice and say, what is it, please, Alice? And she goes, 92. And you're like, great. Now what do we do, right? So there is a lot of things to figure out around the way you structure the cryptographic primitives here. And it's an open question whether this is even reasonably possible from just the data part, just the data itself, not throwing machine learning on top of it. So, cool, all right. Thanks, everyone.
Actually, can I just gate crash some? I wanted to say that I actually disagree with Eves, that you or maybe you can continue that over beers, but
running out.
yeah.
Nice use of the mic.
I know, right? So, hello everyone. Let me first introduce myself. I'm Arnie. I am a machine learning engineer at Flipboard. I also co-organize a meetup, like I mentioned, with Eves. And I'm going to be presenting a talk on something pretty buzzwordy, like counterfactual evaluation. And it's especially buzzwordy because last year I went to NIPS, went to a workshop, and I found that this is a problem everyone's talking about. And then went to Rexis and found that this is an even bigger deal. So I'm going to be talking about counterfactual evaluation of actually, that's a typo. It should be counterfactual evaluation of online metrics. I'm sorry, that was terrible. Started off with a bad note there. All right, so let the timer begin. So this is how I see machine learning being done in production. We get some training data. We define some loss, some log loss, root mean squared error. Then we optimize over that loss. And then we try to convince ourselves that optimizing for that loss was the right thing to do. And then we launch an A/B test and hope that, oh yes, that perplexity that I decrease will help with the click-through rate or whatever engagement that the company actually cares about. That's how machine learning is done, really, in production. We make a couple of assumptions in this world, right? First assumption we make is reducing the log loss or root mean squared error actually increases the metrics we care about. This is usually true when you're a startup and your first algorithms are kind of crap anyway. But when your algorithms start to get better, you find that they're actually not that correlated. The second assumption you make is that the probability distribution of training and the production data are the same. Now, this is a problematic assumption because most of the systems that we deal with in production are user interactive systems, like search engines, recommender systems, ad systems, what have you. What that really means is you only get feedback on things you actually recommend to the user. So imagine a search engine. You only get feedback on things you show to the user, and because of that, you get Simpson's paradoxes. So what you observe in your data is you get a triple of X, Y, and delta, where X is the user context, what you know about the user and whatever the user was doing in the session. Y is the output that you showed to the user under some algorithm Q null. And delta is the click or reward that the user gave you. So this is a classic contextual bandit problem. So you only have partial information. And technically, it's very similar to what an A/B test really is. So in an A/B test, what you do is you segment the users into A and B uniformly. Then you show Y feeds to one set of users under Q null algorithm. And then you show Q prime under a new algorithm, Q tilde. And then you compare some utility. Utility could be something arbitrary like average time spent or click-through rate or whatever your company cares about. So that's what you do in A/B tests, and you try to say, oh, okay, J was higher than I, so that's a better algorithm. This is a simple problem, right? You have X, you have Y, you have delta. That's a supervised learning problem. Let's learn delta. How hard can that be? All right, let's try to model the world. And let's say you do learn a delta hat, a reward predictor. If you do learn that, you can simulate A/B tests offline, right? Because for any new algorithm Q tilde, you can just generate the Y1 primes. Like that's going to be your arbitrary feeds. And because you have a reward predictor, you can just simulate that. And you can compute the A/B tests like offline. This has problems because reward predictor is actually really hard to predict or just estimate because of modeling bias and the sampling bias, which is the biggest problem. Because your data only ever saw outputs of your Q null, of your algorithm that was in production before. So let's do counterfactual evaluation or reasoning. Instead of looking at your data and trying to understand what is it, you actually ask the question, what would have happened if you had shown a user a different item? And that's what you do in off-policy policy evaluation. What you really do, I know it's a bit of math, but you get some users under PX distribution. You have some Q null algorithm that generates the feeds, and then you observe some reward over them, and then you estimate your utility, your average time spent over, by just averaging over the rewards that you saw. Now, for a new policy, what you want to do is just replace this with a new algorithm, the Q tilde. How do you do that? Well, if you forget all the math, the one thing is just here, you can actually do a simple trick, multiply by Q null divided by Q null, and you actually get an importance sampling kind of problem. And notice that if you do this, everything can be evaluated offline as long as you know what this Q null y given x is. Q null y given x is called propensity, which is what this algorithm is called, inverse propensity scoring. And Q null, what it really says is the probability of a yi being shown to the user under your previous algorithm. So this is not a new thing. Criteo had a great presentation at Rexis on how they can predict revenue. Yahoo predicted like click-through rates and like arbitrary internal metrics arbitrarily well just using offline data. And Microsoft has managed to predict click-through rates just using offline data. So why don't we do this? There are a few difficulties in implementing this, and I'm going to mention that next. So one of them, as you saw, there was a Q null y given x at the bottom. That means we need to actually log these. We need to store whatever these probabilities for each item that we show to the user, or have a system that can replay past recommendations easily. Also, because this is in the bottom, you need to have a non-zero probability for all the candidate items for the new algorithm. And that can be quite problematic because most systems that we have in production are deterministic. How do you make a deterministic system stochastic? Well, there's something called Placket-Loose, which I can mention during Q&A if anyone's interested. So anyway, the summary is IPS allows us to evaluate new policies without having to launch any A/B tests or productionize our code. Because we can evaluate, we can optimize. This is the reinforcement learning world. So, one of the cool things about reinforcement learning is you're using human language. You're talking about time spent and click-through rates instead of root mean squared errors. You can actually, using this, you can also do constrained optimization over tangible quantities like CPU time or money. Also, most importantly, if you do that, you can, when you have an algorithm and you report it, you can actually tell your product manager that I expect to increase click-through rate by 10% instead of the perplexity went down 20%. I don't know what that means, but that's what Anyway, that's my talk. If you have any questions, let me know.
Where are the mics? I've got one. Can you pass it over?
Also, I cheated. I have a few slides that I skipped. I'm hoping that someone asks a question that lets me show those.
I guess my question is, what are the slides that you skipped?
Perfect. Great question. Actually, it's more of an example on how, what is it that makes it counterfactual? But essentially, it's a standard problem. This is a problem stolen from Torsten Joachim's slides. Essentially, if you have a data set like this, where some patients survived after given some treatment for heart attacks, if the FDA comes to you and says, what is the best treatment for a heart attack? You can't actually answer that. Because if you just look at this data, you would say, 3 out of 4 people that were prescribed drugs survived. So maybe we should be prescribing drugs for heart attacks to everyone. But that's obviously not the right thing, right? And so, yeah, what I really wanted to say was what happens is the problem gets much easier if you had that table. And these are called counterfactual estimates. And that is what we are trying to do with trying to figure out in the search engine recommendation world. Can we predict what item would have been clicked? If we had shown the user something different, can we still estimate whether they would have clicked on it or not? There are more skipped slides.
Sorry, can I ask one more question?
Sure.
Yeah, a real question.
Perfect. Great question, by the way. This was the best question ever.
Perfect. Yeah. I'm just kind of curious, and I know you can't answer this definitively. The examples that you used of the company's very, very big data, how hard is it to apply this to a smaller data set?
first question to that, like, what do you mean, like, smaller data set? Like, do you mean smaller logs that you have, or?
Yeah, like I'm wondering at what point can you start reasoning about counterfactuals given, say, like 1,000 points, 10,000 points, and I know it's based off of the complexity of the problem,
Yeah.
but just as a, I don't know, rule of thumb.
So it's a difficult problem, right? Like what you're really trying to do is you're trying to approximate A/B tests, right? So if you, like, however many samples you need in your company to figure out confidently, like, oh, it takes like a week long for me to figure out whether the A/B test is different or not, like, you probably need the same amount of data, like, offline. I think the problem is actually not, even for smaller companies, the problem isn't the data collection, it's actually what needs to be collected. And the problem is, no one collects this. Once you recommend something to the user, it's gone, right? And if you can collect that, you're in business. But if you're a smaller company, it's actually much easier to collect that because you can just make a change. But it's very hard to tell someone at Google, hey, you know what? I want to collect all the things that I ever sent out to all, it gets more complicated.
Hello? Okay, so I have a question here. It's kind of related to that. I'm not going to ask you how many samples I actually need, but like when you do that transformation, like in the important sampling one, you introduce an approximation. So that's an approximation. I'm not going to ask you how many samples you need to actually get a good approximation, but is there any way to know that your approximation is actually good enough offline as well, instead of actually having to test it online?
So that's actually a very good way to test because we know the click-through rate of, like, okay, let's say the simple thing. Flipboard cares about time spent in app, right? We know how much time was spent today in the app, right? I can just have a model that looks at the last few days and just see how close I got. So, I could just try to figure out how good my approximation is, but asymptotically, IPS is guaranteed to converge to the click-through rate or to the whatever metric you care about. However, there's a problem. That's why, at Rexis, you probably saw as well that there were papers on SNPs and NIPs and what have you, like those things. Those self-normalized inverse propensity scoring, that's what that stands for. And that one converges a lot faster. So, but the good thing is these things, because you're dealing with real data, you know how well you're converging because even today, you know what your click-through rate was. You just use your offline data to see, can you predict that?
Yeah, because just knowing that it converges is not good enough. Like Newton method converges faster than gradient descent, which in theory converges faster than stochastic gradient descent asymptotically. But
yeah, so that's why there's a lot of work being done. And honestly, in the last week, I tried to implement this for Flipboard. It's super easy. It's literally an importance sampling problem. And another key thing is, I started off with like modeling the world. We actually sidestepped the problem. We never actually try to predict this. You're like, okay, you know what? I assume delta is a complicated function. Screw it. I'm not going to bother. I'm just going to do importance sampling.
So we have time for one more. Yeah, go for it.
Did you see any examples of like complex implementations of this? Like, let's say, for example, you have an A/B test and you have a bunch of different things on the A/B test. Like, let's say in an email, you have different button sizes, text, colors. Like, are there implementations of this that have those varying levels of complexity that you saw?
So that paper right there, what it compared was, this was Yahoo front page from 2011, like Yahoo News. Like they were actually trying to figure out whether they should show 3 articles or 7 articles on the front page. So that paper actually, the first paper that did IPS, did a very complicated tests, like UI tests there. So, all right, cool.
Hello. What happened? Isn't working.
Yeah, so she's going to be your timer.
Oh, okay, that's fine.
I will give you signal fingers for how many minutes have gone by. And if I do this, it means speed up.
Yeah, that works.
Are there any other signals which you would like?
Yeah, so I would like to advertise a meetup around modernizing. So.
Yeah, you can to introduce yourself, give the meetup, and then signal to her when you're ready to like start the time.
Oh, okay.
I'll get this set up into percent.
Okay, my name is Kenneth Odo. So I organize a couple of meetups. I'm a software engineer here in Vancouver, and can you hear me? Oh, okay. Can you? No, not yet. I've not started. So. Okay.
You're not speaking fast enough.
Okay. Oh, okay. So like you see, the first presentation was discussing about homomorphic encryption, and I have we're organizing this cryptography meetup. So it's at somewhere in Gastown, and it's on November the 22nd. So we are going through this Stanford professors Dan Brown on cryptography. So we're going through this. So we're in chapter 5. I think that topic is in chapter 20. So we will get there soon. So and it's very rigorous. So and and I'm also speaking tomorrow at the cargo meetup. So that will be applying image segmentation to oil exploration. So and so I'm expecting you should also come out for that. So you can go.
So you're gonna have to do the button hitting unless you want me to. Just hit the right arrow.
Oh, right.
Will I need to do that for all of them, or will that just kick it off?
No, you'll have to do it for all of them.
Oh, okay.
Do you want me to do it?
Oh, I can do it actually. So my talk is about compressed sensing using generative models. So compressed sensing is, so the topic, we want to know what is compressed sensing and what is generative models. So compressed sensing is a way of recovering information from a set of signals you've done. So and then taking out for instance, if you have this as a set of measurements, and this is a matrix that helps you map it, and then this is the value you're recovering. So you have like an underdetermined system. So that's where you have the number of rows in the matrix more than the number of the columns in your conversion matrix. So there are a number of applications of compressed sensing and like dimensionally reduction techniques. So this is all about having data in different forms. So because, for instance, if you have a data and maybe you do like an FFT on it, Fourier transforms on it, then some seasonality information will become more visible than that kind of stuff. So things like anomaly detection or blind source separation, like independent component analysis, and you're trying to identify the source of things. And then, for instance, if you have a context of this sort, the number of you have it like you have a kind of a matrix. This is what you're trying to recover, and maybe you have a matrix B that has the initial signal. It could be in a different dimension. And maybe you want to get even a lower representation of this that may have the same information as this contains, but of a different representation. So compressed sensing handles this kind of problems quite well. So you can actually extract that information you may want, and then this is just to show you and when you have the underdetermined system, you have infinitively many solutions. And then the point is getting what's the right solution, you may have to impose a structure on your problem. So the number of structures you can impose, so like sparsity, orthogonality, symmetry, or smoothness. So for instance, like sparsity, if you zero out some part of it closer to the null space, you may end up getting some of those. Orthogonality, if you want like an inverse operation, maybe you want an inverted matrix to get the reaction. So in that context, a transpose of the orthogonal matrix will actually be like an inverse. And then symmetry will be what you use like in fast Fourier transforms, because you have this kind of undulating stuff. So now there's some conditions for estimating those kind of matrices. Like in this paper, this work is based on. So it's like they did some research on compressed sensing using generative models, and they realized they were able to achieve quicker run times because they were able to get this property from the generative model, such as restricted isometric properties. So this is actually having some autonomy to impose sparsity, and then there's this restricted engine value stuff. So this is actually having a thin veil distribution. It's like having a distribution that is as long enough and very close to zero. So if you sample from those places in the weight of your neural networks, you're more likely to get these benefits. And there's actually a paper out there by Charles Martins. So this random matrix theory. So yeah, in that regard. So now variational autoencoder is one of those. So variational autoencoder is just having a mapping from one spatial learning functions that maps the input data to some latent space, and then learning another function that gets it back to that space, and then checking the reconstruction error. And then, but it's different from variational autoencoder where you have to learn these probability distributions of how this space was formed, and then how the latent space was formed, and then you do this kind of KL divergence in mapping this kind of relationships. So, yeah, so this is just, when you have this latent space, you can actually take samples from this latent space and then get the output in that. And then when you do this, there's this reparameterization trick. So because you cannot actually differentiate through a random process. So you have to like have parameters representing the process you're trying to sample. Like Z is the latent space, and these are like the parameters. So you can differentiate on those parameters, and that's how you achieve those. Then the GANs are actually having this discriminator and generators where they have a zero-sum game, and then you have this like game theoretic principles. So, and then I won't go into that. So there's some, so imposing structure on your problem helps you. It's a way of doing like regularization. So you're imposing a structure so you can narrow down the infinitively many solutions. Now, in this experiment they did in the paper that I started with. So you can see from this experiment, you can see that sparsity had the largest impact, but regularization already, with like variational autoencoder, already had some number of experiments. At 50 number of measurements, you already have 0.2 reconstruction error. That's the error between the inputs and what you derive when you do your autoencoder. So, yeah, and so like an extension of the work may be like using Westermann method instead of KL divergence. So you can model distribution and then using normal distribution so you can have a closed form for your clear divergence. And then, yeah, representational, and then the number of errors you try to, when you do those variational autoencoder, the measurement error will be the error of getting these measurement signals. Then the optimization error will be the error when you're doing this clear divergence. And then the representational error will be some errors in your models, not being able to capture the entire properties relationship in your data. So yeah, so and then these are some of the references that we could have. So this is a very quick one. And then, yeah, I think at this point, these are some of my past thoughts I've given over this 2013. So I'll be.
A minute left.
Oh, I was so fast. Really. So, yeah. So, for instance, if you're imposing a structure using like L1, you have this sparsity. You may not have a closed form, but L2 will give you smoothness. But the smoothness doesn't guarantee that that result is any better. It's just like more differentiable. So, and then, yeah. So that's all.
Okay. Questions?
If you can go back to I think one more, or actually a couple more. It's the plot, yeah, this right here.
Yeah.
The number of measurements, what does that mean?
It's a number of inputs for the training size.
Okay, but is it of the same image or is it of like different examples?
Oh, is because the image is an input and the same image is an output.
Right, yeah.
Yeah, so just that image, each of those pairs.
Okay, perfect, thank you.
Yeah, the pairs of the same image.
So I have a question. So in compressed sensing, you have, X is supposed to be a sparse signal. And
sparsity is one of the structures.
Yeah, one structure, yeah. You can have different definitions of low complexity modules. But so my question is, so A, the matrix, the measurement matrix, that's the output of the number of measurements. So the number of measurements, at least in that context, is the number of rows in A.
Yes.
So when you take variational autoencoders or GANs, like you mentioned that this is the number of training samples, I don't quite get the.
So if we start from like an autoencoder, so that A would actually be the matrix that leads you to the latent space from the inputs. So and then another A of its form, we take it back to the reconstruction. So if you can reason it, it's like a dimensionally reduction matrix in a GAN. So but the GAN actually, as the paper claimed, imposes those two structures, the restricted isotropic properties, where you have this orthogonality. So I think the benefit of this orthogonality is you just have to take transpose to get an inverse in case. So.
Yeah, I don't know how that actually relates with. I don't know the second condition, but the restricted isometry property is a fairly standard one. It basically means that the operator like A is roughly an orthogonal transformation with when you consider the k-sparse signals. So there is a k there that tells you the level of sparsity. So what I would be curious to know is like, how do these variational autoencoders or GANs behave with respect to sparsity as well? Like, how many measurements do you actually need for a given level of sparsity to actually allow you to recover the signal?
In the paper, they didn't give. In the paper, they give some kind of lower bounds. So that's where the second condition comes in. The restricted, where you have these sample the weights from a thin veiled distribution. So they said if you do that, you are obtaining some sparsity, but you are as far from the null space so it's like you're not zeroing everything of that sort. And they said that gives you some guarantee on the number of training samples you would want. So, but I didn't have time to write the theorems. There were two theorems they had claimed. So I think there were two theorems that they had claimed that where they got those properties, and they had it from using GANs.
Cool, thanks.
Anyone else? Cool. All right. Let's thank the speaker again. Thanks, Kenneth.
Well, now it's great. Okay, now we are.
Now we are.
Yeah. Put the mic on the other side because you're going to be pointing at it.
Sorry. Watching this side.
Try that.
Hello, hello.
Is this the opening?
Yeah.
Yes.
Okay, so this is a very nice sedge into going into the bar because this is a more relaxed talk. There are no formulas, and it's a more personal story about a textbook on feature engineering I'm writing, and trying to also share the content a little bit of the book, but for the most part, trying to convince you that you can also write a textbook. It's an interesting personal journey. And try to meet also a little more people in Vancouver. It's already a year I'm living here. So the book is called The Art of Feature Engineering, Essentials for Machine Learning, and it's supposed to be coming up in 2019 published by Cambridge University Press. So this is a what, why, and how type of talk. So, so my background, I did computer science in the math department in Argentina, then I did a PhD in New York in natural language generation using weakly supervised learning. I consider myself a good ML practitioner, not an ML researcher. And natural language processing traditionally uses tons of feature engineering. I have a small consulting company here in Vancouver. So after my PhD, I joined IBM Research, And I was part of the original team that built the Watson system that participated in the Jeopardy shows in 2011. And that showed we needed to make a system that ran really, really fast. So for that, we used simple models like logistic regression, but we did tons and tons of feature engineering. And for that, I actually wrote a domain-specific language for feature engineering that allow us to do something like this. Each of these boxes are different feature engineerings, and these are combinations of models. All this is in the article in the IBM Journal of R&D. If you are interested, I can send you the article, a preprint of the article. Okay, so from there, I really got the value of feature engineering. I was interested on the topic. 2014, I went back to Argentina for a semester, and I taught a class on machine learning over large data sets, where we cover Apache Mahout and Hadoop. And when I was preparing a lecture on feature engineering, I realized there were no books on the topic, and even more like the textbooks really have a few paragraphs, and it's not much information. So then in 2016, I was in New York accompanying my spouse, Annie, and I was in a spouse visa, so I revisited the idea of writing a textbook. And the main concern when you think about writing a textbook is, do we need more books? There are so many books already, and why go through all the pain and suffering of writing a book if there is no need? So for that, then I started doing some background research. Yeah, some background search. By that time, Alice Zhang's already had a book, but the book was really heavy on manifolds, and it was very theoretical. And so I started also looking into potential publishers, traditional sources, papers, textbooks. But one of the interesting things about feature engineering is that there are plenty of value on non-traditional sources, videos, Quora, Stack Overflow, blogs, course description. So I went through all that material, and I came out with a plan for the book with a focus of helping practitioners. Yes, people are already familiar with the algorithms, but will need some help trying to squeeze more value from them, and then helping approach new domains. So the book has two parts. The first part is domain-independent methods, and the second part are all case studies on very popular domains. So around 200 pages, 10 chapters. The first part, in the introduction, I discuss a proposed feature engineering cycle focused on trying to avoid as much as possible overfitting. I mean, feature engineering is like an overfitting hell. The chapter 2, I discuss how to handle the features all together. So normalization, histogram, outliers. Chapter 3 is the only one I have already finished. It's computable features, so how to expand features, computable imputation kernels. Actually, that's the only chapter I have reviewed by Kenneth, so thank you. And then chapter 4 is how to reduce features, so feature selection, dimensionality reduction, embeddings. And chapter 5 is advanced topics like encoding variable length feature vectors, deep learning, and feature learning. Then the domains I do for the part 2 are it's quite interesting because I found a task that can approach with different methodologies. That is predicting population of cities. And you can use the DBpedia and use a semantic graph, but you can also use a time series about how the data has changed to do the same thing. You can use the text descriptions or you can use satellite images. Then I have a last other domains with video, GIS, and preferences. So once I have the table of contents, I can start approaching publishers. And when you told them you want to write a book, they will send you a template for the book proposal. And some may ask you to ask a sample chapter, and I went through a few, and at the end I decided to settle for Cambridge. Most proposals are the same. They basically want to know your reasons for writing, the table of contents, the target audience, marketing ideas, and proof that you can write the book. And basically, you have to write about 20, 30 pages convincing them that the book is worth it. Afterwards, they will have it reviewed by peers. And when you mention that you want to write a book, they actually start asking you to review things. And you learn a lot about how to write a good proposal from seeing this. The hardest thing is to write a sample chapter. And in reality, this logistic of finishing a full chapter before moving to the next one is something I'm having a hard time right now. And the main technical thing I would like to share with you is, just a comment about money. Writing textbooks doesn't make money. So if that's what you are interested in, not really that direction. And the main thing I want to say is that if you do feature engineering, you most probably will overfit. So it's common to say, well, you have a final test set, and then you evaluate your model there. But I'm proposing saying, well, make 2 feature sets, a good one and a conservative one, because if the best one fails, then you are left with nothing. So if you have a long stream of data, of course, you don't need to do that. But so I'm still looking for some more chapter proofreaders. Just ping me on Twitter if you are interested. And to conclude, I am giving an AI in production coming talk on the semantic graphs stuff, so the chapter 6. And we will see some sample code there, and hopefully in December or whenever it's available. Thank you.
Great. Are there any questions? Yves, go for it. You have a mic.
So I actually have 2 questions. One is more specific to this, to the subject of feature engineering. So many people say these days that
you don't need feature engineering because we have deep learning.
Yeah, why don't you just throw deep learning at it and learn the features? Why are you doing engineering? So do you believe that does the trick? If yes, why? If not, well, why?
So what I wrote on my proposal was that practitioners track research maybe 10, 15 years. And yes, the research right now is in deep learning that doesn't need feature engineering. But the practitioners are still, and I'm thinking about smaller practitioners, like startups, so people who have a little amount of data. If you have tons of data that you can do deep learning, then you wouldn't need this textbook. That's definitely the case.
And so why not, now actually relate to books, why not like self-publishing, like say, for example, Kindle Direct Publishing, just one example.
So I did consider that a lot, but because to me, one of the main things was not to write a book unnecessarily. So getting buy-in from the publisher for me was important to say, okay, it's worth writing the book. But the other thing I really toyed was with the idea of doing a ransom system where you ask people to give you money and you start writing a chapter and releasing it as they give you money. So I was more, I mean, to me, like writing the whole thing is a monster. So I didn't want to do it if it's not really useful.
Any other questions? Okay. So let me know if you have any other
questions. Publishers are much nicer than I thought. I mean, the editors actually, they want your books. That's something I didn't expect it. I thought they were really like, but no, they're actually very nice people.
Thanks for the talk. Had a quick question regarding the feature engineering. Moment you add a feature, you add an order of magnitude to your data. And so let's say you are pre-processing in some electromagnetic or some domain, which means you require some other tools, say electromagnetics or some other tools. And it becomes a problem or you get into dependency hell. Moment you start pulling in tools from other domains, how?
Okay, so I understand two directions of your question. So one is you need a lot of domain knowledge, domain tools, domain things to do feature engineering. Yes, and there is a lot of discussion about whether you can do anything domain independent in feature engineering. Yes, but there are still some things that are somewhat domain independent or at least transferable across domains. And the other thing is about the software engineering aspects of doing good feature engineering. And that part is actually, we are lacking good tooling for that. clearly this domain-specific language I wrote back when I was in IBM, that it was proprietary software and never was used by anybody else but the IBM team, is still quite needed, because you are doing the software engineering and you have this featureizer and you want to compare different versions and different featureizers, and it's very easy to forget how the whole thing went through. So it's not only the dependency help, but also just this living code that correlates with data and stuff gets very messy.
Is that tool available open source?
Nope. And the people, they are already left IBM, so most probably it's gone in the waste bin of bits.
Thank you.
Any other questions? Oh, if you put your hands up ahead of time, I can bring you a mic earlier, just to let you know.
Just a really quick one. Could you go back to your Twitter handle? So write it down.
Sure.
So I think I'm up. So my wife likes to complain that it can be hard to find people with good sort of data analysis skills. Some kind of critical thinking, but essentially like an ability to like quantitatively dissect a data set and start to get, like business insights out of it. And it strikes me that the properties of a good feature engineer are probably really similar.
So I agree with your wife and your comment, but people don't even try. Yes, so one of the things I say in chapter 1 is you have to start doing exploratory data analysis. And from there, you have to come up with a featureization and with an algorithm. And after you train, you have to do error analysis. And people just look at the number, like they are doing RMSE, and they just run with it and change the algorithm and change things. Like, no, stop, look what you have done. That type of stuff is what I'm trying to get through in the first chapter. That it's not just that error number that will help you improve the algorithm. And definitely model shopping, like just trying everything in machine learning library is not the way to go. So some people have more skill on the analysis, but everybody can get better if they actually try, right? Maybe.
And do you think then if somebody went through this process of learning, for feature engineering, they would sort of simultaneously learn some transferable skills for data analysis? Or do you think that those skills are a prerequisite?
No, these are just the same skills. Yeah. I mean, it's just analyzing a data set and getting insights. I mean, to me, the whole feature engineering process is an internal process on the practitioner. That's why the overfitting happens, because you are overfitting your understanding of the data, and the data may mislead you because it's a sample, as Arnie was mentioning.
Thank you for the talk. Can you describe a day in the life working for Watson, specifically on such a large project? How did they ensure that new features that they were adding actually contributed to the total performance as opposed to?
Sure. So our big success was in the fact that we have 60,000 historical questions for Jeopardy, and they were locked down so nobody can use them. So one of the highest people in the team, a manager, took that data and said, well, nobody can look at it. And they start releasing it in lumps of 2,000 questions. And then we will spend for like a month training like crazy on the data we had so far, and then test it on these fresh questions and realize that we have overfit like crazy. And spend 3 days all locked down in a room doing error analysis, question by question, to see where the system fails and hating our lives. And then, come up with hypotheses, improve, and test on fresh questions, and so forth, so on. But the main answer is Tannenbaum, when I was studying in MIT. It's like drinking from a fire hose. You're not really going to like it. So it was a very stressful project.
Great. Is it on? Great presentation. A couple of things because I actually do a lot of feature engineering, mostly because I work on topic extraction, and very often you get bug reports saying, why is this article tagged with that? And you can't say my deep learning model just decided the embedding was right for it, right? But another perspective to it, like, is the Bayesian perspective. Like when you're dealing with this, when you're dealing with small data, do you also consider that a form of feature engineering because you're trying to enforce your prior knowledge, trying to model, what you know about the problem, and then you're just kind of curious to hear your point of view.
So I sort of consider it as another way of adding domain knowledge, but it's not covered in the book. The same way that deep learning architecture tweaking, which in a way in deep learning you stop doing feature engineering, but then you start doing architecture tweaking, is not covered either.
Yeah, the reason I'm asking is mostly because a lot of in the text world especially, like when you're dealing with things like topic models or latent tertiary allocation and LDA kind of methods, it was really more of a feature engineering driven idea. Like you look at the problem, you enforce the assumption that, hey, I know a document only has 6 topics.
Actually, I just realized that my LDA section describes the generative model and stuff. So yes, actually I have it on the book.
Oh, perfect.
Yeah.
Great. Maybe I can review that too.
Actually, I think my question is going to turn to be kind of similar, but I wanted to get back to the deep learning obsoletes feature engineering idea. So in deep learning, you do bring domain knowledge to the problem because you have to choose an architecture. And the fact that you would choose a CNN to work on an image classification problem has a lot to do with the structure of images and your knowledge of that and so on. Do you consider that choice of architecture even to be a kind of feature engineering? It's I would call it domain knowledge. I don't know, do you discuss anything like that?
I do consider it, yes, and I do think there may be some transferable skills, but the textbook I'm writing it should be kind of boring for a big percentage of the advanced data science team group. I mean, it's a textbook of these techniques that have been kind of distilled, and people don't want to put it in a textbook format because they are not necessarily that sexy. I mean, take logs on the target and the feature, it actually does work, but it doesn't sound like you should write a book about it. Oops.
Cool. That's the end of questions. So let's thank Pablo again.